The next speaker is Abdul Rahman. He's a second-year PhD student at Purdue. His research interests focus on synthesizing the network using artificial intelligence. He is looking for internships, so if you have any opportunities, please talk to him.
Hello, everyone. I'm Abdul Rahman. Today I'm presenting our work, Transferable Neural 1TE for Changing Topologies. This work is jointly done by researchers from Purdue University and Meta. Traffic engineering pipeline takes as inputs a set of traffic matrices, a set of capacities, and a set of predefined tunnels, and all of these will be fed to a centralized SDN controller. Common examples are ABB controller, SWAN, and B4. This centralized controller has a global view of the network. It optimizes a network-wide objective, something like minimize link utilization, where it employs linear programming to route the traffic. However, using LP solvers in the SDN controller has two main drawbacks. The first one is that input traffic matrices do not fully capture the actual traffic matrix. And LP solvers do not have any way to cope with prediction inaccuracies, eventually resulting in suboptimal routing. The second problem is that LP solvers do not really scale to large topologies. So the community has recently shifted towards using neural models instead of LP solvers. Last year we saw DOT and TEAL, and that's reasonable because the neural models are somewhat promising. First, because they can compensate for prediction errors, yielding eventually better routing. Can you please go to the next slide? Okay. And they are also faster and can scale to large topologies. However, there are some challenges that neural models need to address. For instance, networks evolve continuously for multiple reasons, including organic growth, unplanned failures, and planned maintenance. The figure on the right illustrates the variation in the number of links over a 4-week period from a private real cloud WAN. This figure shows that links addition and failures happen frequently. However, existing neural TE schemes focus on fixed topologies and fixed set of tunnels. Thus, they do not generalize to topologies outside training set. For this, we present HARP, the first neural TE scheme that can handle changing topologies. Can you please go to the next slide? HARP is by design transferable, where it ensures key invariances to natural input transformations like reordering or relabeling of tunnels. Also, HARP's neural architecture is aligned to the optimization model. In terms of performance, HARP outperforms classical LP solvers. Depending on the traffic matrix predictor, HARP generates 5 to 13% lower average maximum link utilization on average. Also, HARP is 100 times faster on large topologies compared to the state-of-the-art neural TE schemes like DOT and TEAL. HARP is 34% lower generates 34% lower MLU than DOT and TEAL on average, while being close to optimal MLU despite the significant topologies and failures seen in testing that are not in the training. To motivate the design of HARP and explain where existing neural models fall short, let's consider why explicitly modeling topology is important. And for this, let's consider DOT, which is basically a fully connected neural network that does not model capacities, tunnels, or topology. To be concrete, it takes a fixed set. Okay, please move to the next slide. It takes a fixed size traffic matrices and generates routing on fixed set of tunnels. However, when tunnels or capacities change, DOT does not change its routing. And the topology to the right, we see that the allocation is still the same, though C1 is greater than C2. And in this case, the upper tunnel should carry more traffic than the middle tunnel. But DOT simply not able to distinguish these two scenarios. To be precise, for the same input traffic matrices, DOT generates the same routing, regardless of tunnels and capacities used. A second issue to consider is why preserving invariances is important. And for this, let's look at these two topologies, which are basically identical, except that the tunnels are relabeled or reordered. This relabeling has no effect on the routing. However, existing neural TE schemes like DOT and TEAL do not guarantee identical routing in these two scenarios. In fact, preserving invariances is a prerequisite to generalize to topologies unseen in training. While designing HARP, we had two principles in mind. The first one is to ensure invariances to natural input transformation, like node relabeling, tunnel relabeling, and traffic matrix transpose. The second principle is to align its architecture to the optimization model. And by this, we mean introduce some components that mimic the iterative nature of optimization algorithms. This serves as an example of the power of neural algorithmic reasoning. These two principles allow HARP to generalize to topologies beyond training. HARP consists of 4 modules. The first one models the topology and capacities, while the second module is responsible for modeling tunnels. The third one will generate initial routing, while the fourth and final one is responsible for iteratively improving the routing. To be concrete, can you please go to the next one? Okay. To be concrete, HARP starts by taking topology and capacities as input and feed them to a set of graph neural network layers to generate a set of edge embeddings. Those in turn will be fed to a set transformer, which will also take tunnels described as sets of edges. Here I emphasize that modeling tunnels as sets of edges introduces an invariance to traffic matrix transpose, in contrast to modeling them as sequence of edges. Set transformer eventually will generate a set of tunnel embeddings. Initial routing prediction will take it from here by feeding the tunnel embeddings alongside input traffic matrices to a multi-layer perceptron, which will in turn generate an initial routing, which will be used to compute network-wide MLU and highest link utilization in every tunnel. These two values, alongside the input traffic matrices and tunnel embeddings, will be fed to a recurrent adjustment unit that is applied k times in order to iteratively improve the routing before generating the final one. We conducted our experiments using 4 datasets. ANANET is a dataset collected from a private real cloud WAN. Giant and Abilene are public datasets, and KDL is a public topology with which we used synthetic traffic matrices. We compared HARP to DOT, TEAL, and Gurubi, which is a widely used LP solver. We note here that all schemes were evaluated using ground truth matrix, unless otherwise mentioned. But before we delve into the results and evaluation, it is essential to provide more details and characteristics of the ANANET dataset. ANANET basically is collected over a 4-week period at 1 minute granularity, where every snapshot has a traffic matrix and a topology. We partitioned the dataset into 78 clusters, where within a cluster, tunnels are fixed, but link capacities change in the form of partial and full link failure. For example, one of the clusters witnessed 250 unique link capacity configurations. But across clusters, tunnels also can change, possibly due to node addition or link addition. For example, we noticed that 20% of last cluster's tunnels were not present in the first cluster. Here I emphasize that prior work has only, I would say, experimented with static topologies without changes. Can you please go to the next slide? To evaluate the ability of HARP to perform well in such dynamic conditions, we trained HARP on the first 3 clusters, validated it on the next 3, and tested it on the remaining 72 clusters. And to explain our metric, normalized MLU, it is obtained by dividing the generated MLU. Can you please go to the next one? It's obtained by dividing the generated MLU divided by the optimal MLU, where the optimal is obtained by a clairvoyant LP, and it's only needed for plotting. As we see, HARP is within 20% of optimality, 98% of the time, despite significant tunnel and topology changes outside the training set. We then compare HARP to DOT, where they are trained and tested on the same cluster. We see that HARP generates significantly lower MLU compared to DOT. To be concrete, HARP is on average generates MLU that is 3 times lower than that of DOT. And this is mainly because DOT assumes static link capacities, where it lacks any mechanism to handle partial and full link failures. This makes working with DOT across clusters even more challenging. We then gauge the ability of HARP to compensate for prediction errors. We compare HARP to Gurubi on the predicted matrix. As we see, HARP outperforms Gurubi and generates 99% less MLU on the 18th percentile. We show in our paper that benefits are even greater with our predictors. Please refer to our paper if you are interested to see the results. Here we hypothesize that HARP learns to be robust to prediction errors. We then demonstrate one of HARP's invariances to natural input transformations. In this experiment, HARP, DOT, and TEAL were trained with a set of tunnels. Then 2 experiments were conducted. In the first experiment, we used the same training tunnels in the same order. And as we see, the three systems perform well. However, in the second experiment, we used the same training tunnels, but relabeled or reordered or shuffled. And as we see, only HARP retains its performance, while dot and teal generates 1.5 times higher MLU. Finally, we compare HARP to another version without the recurrent unit to showcase the importance of aligning neural architectures to the optimization algorithms. We see that HARP makes significant improvement due to the presence of the recurrent unit. In fact, on average, HARP's MLU is 1.6 times lower than that of HARP without a recurrent unit. Please refer to our paper to see other experiments where we show HARP's ability to handle failures outside the training set. We conducted experiments with full link failures and partial link failures, and we also presented computation times to showcase the ability of HARP to scale to large topologies. To wrap up my talk, I presented HARP, the first neural TE scheme that can handle changing topologies. HARP is by design transferable across topologies, where it preserves key invariances to natural input transformations. Its neural architecture is aligned to the optimization model. In terms of results, HARP outperforms classical LP solvers like Gurubi, where it generates 5 to 13% lower MLU on average based on the traffic matrix predictor. At the same time, HARP is 100 times faster on large topologies than classical LP solvers. HARP performs well even with topologies or failures outside training data, while being close to optimal in all cases. Finally, HARP generates 34% lower MLU than state-of-the-art neural TE schemes like dot and teal on average. We released the code of HARP and made it public. This marks the end of my talk. Thanks for your listening, and I'm ready to take your questions.
Let me ask one to get it started. So can you comment a little bit on the latency of HARP in absolute terms? Would it work in the case of topology changes with network failures, for example, link failures? So how much time does it take in absolute terms for HARP to finish?
The largest experiment, just to repeat the question, how long does it take to recompute the split ratios or the routing? The largest topology we experimented with is KDL. It's around 800 nodes and 900 links. It takes, on average, I believe, 3.2 seconds to generate the final routing, while Gurubi needs around 300 seconds.
Hi, Matt Rowan from Adelaide. So first up, I'd like to commend you on taking into account network changes. I think that's really important and something you don't usually see.
I'm sorry, can you please repeat?
I just want to commend you on taking into account network changes. That's a really important thing and really cool. But I'm a little concerned about comparisons to LP solvers. So you said use Gurubi, but you didn't really say what the problem was you're solving. And it's been known for a long time, 20 years at least, that if you set up an LP solver that's designed to come up with this sort of optimal routing based on a predicted traffic matrix, it will do worse than if you use a robust optimizer. So I was kind of interested in what you were doing with that LP solver.
Just to be clear, you are talking about the comparison with Gurubi, right?
Yeah.
Okay. On that one, in fact, it's in the favor of Gurubi in some sense because the topology is known for Gurubi. Okay, it's only gauging the prediction error. But for HARP, it has just learned on something, and then on testing, it has to, say, generalize beyond the training set.
I guess what I'm saying is not about the topology, it's about what the optimization objective is fundamentally and what the constraints are. So if you set up an objective which is based on the idea that you know the traffic matrix exactly, then of course it's not going to do as well if the traffic matrix is not the predicted one. Does that make sense? So I guess I'm trying to get at whether the LP solver is really just a straw man here, or whether it's really doing the best job it could with the prediction problem.
I'm sorry, I'm not sure if I get your question. Can you please rephrase, or just let me rephrase and tell me if I'm understanding right? You're asking about the LP solvers, what it is fed, what it takes, and how it is tested or evaluated?
I mean, Gurobi is just a back end. Doesn't say anything about what the problem is.
Yes, the idea here, we are feeding that predicted matrix to generate some routing and then plug it on the actual ground truth matrix and see the gap between the both, I would say, both frameworks, Gurobi with the predicted matrix and HARP with the predicted matrix.
Okay.
On the ground truth, which is obtained by clairvoyant LP.
Yeah, okay, maybe we can talk a bit more afterwards.
Okay. This is a predicted traffic matrix, but the crux of it is that you generate the routing depending on the predicted matrix, but the loss function is computed on the ground truth. This is in training. On testing, you have only the predicted matrix.